So the previous video, the previous lecture, we saw that when the received signal, that is the method of detecting minimum shift keyed signals were discussed, and we saw that when the received signal is multiplied by phi 1t, when the received signal was multiplied by phi 1t, which is one of the basis functions discussed earlier, and then integrated from the interval k minus 1 tb to k plus 1 tb, we got the result as root eb cos theta ktb. And when the received signal was multiplied by phi 2t and integrated from the interval ktb to k plus 2tb, we got the result as minus root eb sine theta k plus 1 tb. So from this we could obtain theta k tb and theta k plus 1 tb, and we could obtain bk that was discussed, and this process is continued to obtain bk plus 1, bk plus 2, and so on and so forth. Now, since this is obtained by multiplying the received signal with phi 1t and integrating from k minus 1 tb to k plus 1 tb, we can say that this becomes the component or the projection of the signal received in the interval k minus 1 tb to k plus 1 tb onto the phi 1 axis. And remember, since there are two basis functions, it's a two-dimensional signal space. So I can write this as equal to S1. Similarly, since this is obtained as a result of multiplying the received signal with phi 2t and integrating from the interval ktb to k plus 2tb, we can say that this becomes the projection or the component along the phi 2 axis of the signal from which exists in the interval ktb to k plus 2tb. So again, this we get by multiplying the received signal in the interval ktb to k plus 2tb with phi 2t and integrating it from the interval ktb to k plus 2tb, which means that this becomes the phi 2 component, which we can appropriately call as S2. Now this says, or this gives us an idea, and we know, of course, as I said, it's a two-dimensional signal space, and this result, this observation gives us or with the help of these observations we can form a table, and from the table it is possible to get to the signal space diagram and the signal constellation. And once we have the signal constellation, without any effort whatsoever, we can conclude what will be the bit error rate performance of minimum shift keying. So that table we will form first, and then we will go for the signal space diagram. So we have the first column theta ktb, theta k plus 1 tb. Remember, k is taken as an even number, so you can say this is theta 0 and theta 1, or you can say this is theta 2 tb and theta 3 tb, and S1 is here, and remember S1 is root eb cos theta k tb, and S2 is here. Remember, S2 is minus root eb sine theta k plus 1 into tb, and we have the detected bit here in the interval ktb to k plus 1 tb. And theta ktb, the possibilities are for k even. If you recall that phase evolution diagram, the possibilities are theta ktb can be 0, minus pi, or plus pi. So remember, theta ktb can be 0, minus pi, plus pi, and theta ktb can take on values and this is modulo 2 pi. Remember, theta k tb, k plus 1 tb can take on values plus or minus pi by 2 with k as even. So k even means k plus 1 will be odd. So plus or minus pi by 2 rather. So this is only for our quick reference. So let me list down the possibilities here. 0, pi by 2, 0, minus pi by 2, minus pi, minus pi by 2, minus pi, pi by 2. I'm just listing down the possibilities, and you can see that for each I'm just writing the possible values which they can take. Pi, pi by 2, and pi minus pi by 2. I think I have considered all possibilities. Yeah, of course this could have been pi by 2 minus pi by 2, but doesn't matter. That need not necessarily be in any sequence. Only thing is that we have to ensure that we have considered all possible combinations of these two. Now let us write S1 and S2 for each of these values. So when theta k tb is 0 and theta k plus 1 tb is pi by 2, we will get root EB and minus root EB. You can simply substitute it in the respective values, in the respective expressions for S1, S2, and you will see this is what you are going to get. Root EB, root EB minus root EB and root EB minus root EB minus root EB and minus root EB, because cos pi is minus 1 and sin pi by 2 is 1, so minus root EB minus root EB. Now let's see what will be the corresponding BK. And we quickly recall, and for reference I am writing it here for easy reference. So whenever theta k plus 1 tb is pi by 2 more than theta k tb, we can say bk was plus. And whenever theta k plus 1 tb is pi by 2 less than theta k tb, bk is minus 1. So if bk is 1, you can see that pi by 2 gets added to this and that becomes this. When bk is minus 1, pi by 2 gets subtracted from this, and that's what theta k plus 1 tb. So from that we can easily see that since it has increased from 0 to pi by 2, bk is 1. It has decreased from 0 to minus pi by 2. It has decreased by pi by 2. So minus 1. And from minus pi by 2, this is increased by pi by 2, because minus pi by 2 it has increased by pi by 2, and hence you get minus pi by 2. So since it's an increase by pi by 2, bk has to be 1. And then we have minus pi to pi by 2. Minus pi to pi by 2 seems like a transition which may not happen at the if you look at it, but still remember that pi by 2 is minus 3 pi by 2 modulo 2 pi. Pi by 2 is minus 3 pi by 2 modulo 2 pi, which means that this is actually a decrease by pi by 2, because if you add minus pi by 2 to this, you are going to get this. So it's actually a decrease by minus pi by 2, and hence this is minus 1. And likewise, pi to pi by 2 is again a decrease by pi by 2, so minus 1. And pi to minus pi by 2, again minus pi by 2 is 3 pi by 2 modulo 2 pi, so that is an increase by pi by 2, and you get this. So this is how the receiver is going to detect the bit transmitted in the interval k tb to k plus 1 tb. And the same thing, a similar thing can be formulated for the next interval and so on and so forth. Now this leads to the signal space diagram, and remember S1, S2 are the two coordinates of the signal points, and in a noise free situation, of course, assuming noise free conditions. So we are just going to draw the signal space diagram now. It is a two-dimensional signal space diagram. Phi 1, phi 2. We can also call this as in-phase and quadrature. In-phase, quadrature. And you can see that S1 is the projection along in-phase and S2 is the projection along the quadrature phase, or you can say that S1 is the component along phi 1, S2 is the component along phi 2. So root EB minus root EB, and that point represents bit 1. So BK is equal to 1. Root EB. So root EB is this, the other root EB will be here. That is root EB, S2 root EB represents this point, and this is the point represented by this combination, and that is BK minus 1. S1 is minus root EB, S2 is root EB, again BK1, and then you have minus root EB minus root EB, that is minus 1. Rest of it is the same in the sense the combination is the same. So different phase combinations end up giving the same bit. Anyhow, so this is the signal space diagram and the constellation. Now if you speak in terms of decision regions, you see that this region belongs to bit 1 and this region belongs to bit minus 1. That is symbol 1 and symbol minus 1. And we observe that the shortest, the minimum Euclidean distance, so to say, the minimum Euclidean distance is root EB, 2 root EB. This is more than that. So since the distance between two distinct signal points is given by 2 root EB, an error occurs when this is the actual symbol transmitted, but you end up detecting it as this. And compare this now, or of course when I speak in terms of this side, an error occurs when this is the transmitted bit and you end up detecting it as this, or vice versa. Now compare this with binary PSK signal space diagram. Binary PSK is one-dimensional, as we know. There is only one basis function, phi 1 or phi t, if you want to call it as, and the signal constellation is like this. The distance is 2 root EB, and error in detection happens when an error is made when this is the actual transmitter, it is detected as this. This is the actual transmitter and it is detected as this. Any one of these two is an error, and we see that the distance is 2 root EB. You can see the similarity between the two signal space diagrams and conclude very easily that in the presence of additive white Gaussian noise of two-sided power spectral density n0 by 2, due to the fact that an error is represented by similar events in the two signal space diagrams, the performance of minimum shift keying will be identical to the performance of binary phase shift keying. So you can simply use the same expression which we use for the error rate of binary PSK to find out the error rate of minimum shift keying. That is the conclusion as far as the analysis is concerned. Now before I wind up, I will give you the receiver schematics. Receiver schematics we have in fact discussed in words, but I'll still give you the block diagram. The schematics, block diagram of the schematics. Received signal, this is the minimum shift keying receiver. Multiply with phi 1t, I have told what is phi 1t. Integrate in the interval, integrate the product in the interval k minus 1 tb to k plus 1 tb, sample at the time instant k plus 1 tb, which is the end of the integration interval. Second arm, multiply with the other basis function, integrate from the interval ktb to k plus 2 tb. Remember the duration of integral is 2 bit intervals, and multiply, integrate and then sample at t is equal to k plus 2 tb, k plus 2 tb, and these two will be given to a decision, sorry for writing it like that, decision circuit, and the output of this will be the decision. That output will be the decision. So this is the block diagram of the schematic block diagram of the receiver, minimum shift keying receiver. Now once you get BK from this, what happens is the integration here will shift from k plus 1 to k plus 3. To proceed further with the process of detecting the bits, we next integrate this from k plus 1 to k plus 3 tb, k plus 1 tb to k plus 3 tb, and this is multiplied from k plus 2 tb to k plus 4 tb. This continues. Now I repeat the question which I asked. When we do this, should this be multiplied with phi 1t itself or a delayed version of phi 1t? Similarly, when we go for the next integration interval here, should we be multiplying the received signal with phi 2t itself or a delayed version of this? Now this is again, I leave it as an exercise for you. If you go back through the analysis again, you'll be able to find that out for yourself. So that's a task for you. Now this completes the discussion of minimum shift keying, and we will be winding up the course here. We don't have time left because you know that the classes are ending soon, so we don't have time now further to discuss the topic. So I have covered signal detection and estimation after introduction to the digital communication systems, modern digital communication systems. I have covered signal detection and estimation in some detail, and then I have covered coherent detection of the various digital modulation schemes in some detail, and in fact in much of details, and all the error rate performance we have evaluated. So with that we will be ending this course.